Hi, my name is Vivian, and my group members are Javier, Micah, Ryan, and Dalton. And for our presentation, we're doing higher or lower. Electromagnetic induction is the creation of an electric current flow formed through an electric pressure by moving a magnetic field around an electric conductor or moving an electric conductor through a magnetic field. Federer's law of induction is when a magnetic field changes, it causes a difference in the electric current flow, also known as voltage. In simpler terms, a voltage in circuit is proportional to the rate of change over time of the magnetic field in the circuit. And next is Javier.
So for this experiment, we decided to focus on the concept of Faraday's law of induction by creating a simple demonstration. The way we integrated Faraday's law of induction was by observing the voltage and current generated when the number of copper wire loops was changed. So before starting off our experiment, some of the materials we will need to showcase the concept of Faraday's law of induction include copper wiring, a neodymium magnet, an ammeter, and a recording device. Next up, Brian will introduce the formulas and background information needed for our experiment.
For this experiment, we used 3 coil ring sizes of 50, 75, and 100 loops. And for our formulas, the first one we have to calculate is the magnetic field in a coil, which is mu naught, the permeability of free space, which is a constant that is proportional to the magnetic flux density and magnetic field strength in a vacuum, times the number of loops divided by the length of wire times the induced amps. And we will then use that to find the change in magnetic field, which is the magnetic field times the area of the loop, which we will finally use for the law of induction, which is negative n, or the number of loops, times delta phi, or the change in magnetic field, divided by delta t, or the change in time. And next we will go to the demonstrations.
So just to be clear, the demonstrations were in ascending order. So it started at 50 loops, then to 75, then to 100. So as Ryan just said, there's 3 different steps we have to go to. The first step is finding the magnetic field strength of the magnet used. And so to do that, we use the equation of B, which is magnetic field strength, is equal to mu naught times the number of loops over the length of the wire times the induced current. By doing that, we end up getting a number of 8.5 times 10 to the negative 12 Teslas, which is the unit we use for magnetic field strength. From there, we can find the magnetic flux by using that number. You might see, so there's a cosine of 0 in the equation right here. That's actually for in a system where you're trying to actually find what the magnetic flux is, the angle of the magnet compared to the coil does matter. In this case, just to simplify things, we just said the angle was completely perpendicular to the coils, meaning that the angle was 0. Therefore, cosine of 0 is just 1. From that, we ended up getting a magnetic flux of 7.27 times 10 to the negative 15th Webers, which Webers is the unit, the SI unit of, or one of the units for magnetic flux. And it's also defined as a volt over second. And lastly, we then used the Faraday's law of induction. So negative 50, which is the amount of loops, multiplied by 0 minus 7.27 times 10 to the negative 15th Webers over the change in time of the magnet going into or out of the loop, which we found as 0.3 seconds, which gives us a voltage, induced current of, or induced voltage, I should say, of 1.21 times 10 to the negative 12 volts. We can keep going to the next one. I'm not going to explain everything, but the formula is exactly the same. And you can see that as we increased the value of the loop to 75 loops, the voltage increased, and as we increased to 100, it also increased as well. So for 50, the induced current, or the induced voltage, I should say, was 1.21 times 10 to the negative 12 volts. For 75, it was 5.15 times 10 to the negative 12. And for 100, it was 1.13 times 10 to the negative 11. The change in voltage was a bit off for each of them, and that could be to the amp meter reading, that could be to a lot of different things. But from 50 to 75, it was about 3.94 times 10 to the negative 12 volts. And the change from 75 to 100 was about 6.15 times 10 to the negative 12. This means we have an average value of about 5 times 10 to the negative 12 per 25 loops added. Knowing this, we can predict with a decent amount of uncertainty because of the difference in them, but we can predict that adding one loop should add a voltage of 2.02 times 10 to the negative 13 volts. So we could predict, 125, 150, 175, or even a couple different values because we know that average value and how much it should add.
So in conclusion, by using the data provided through the amp meter, we can find that the amount of coil rings affect the voltage and current produced by a magnet passing through them. As the more rings, the stronger the voltage and electric currents will be. Through Faraday's law of induction, we can calculate the number of loops N is directly proportional to the amount of induced voltage in the wire. It should be noted that lowering the amount of time that the magnetic field is changing is inversely proportional to the amount of induced voltage, and it can also be increased or decreased depending on the type of strength of the magnet used.